So in this video, I'm going to go through an alternative method for this question, where we have this car of mass 900 kilos travelling at a steady speed of 16 meters per second up a hill, inclined at arc sine 0.1 to the horizontal. The power required to do this is 20 kilowatts. Calculate the resistance to motion of the car. So we drew ourselves a diagram in the previous video, and we said that, well, the power is equal to the driving force times the velocity. We worked out the driving force as 1,250 newtons. Now at this point you could employ an energy method. Okay, so you could go about this by using the work energy principle. So we would have the initial kinetic energy plus the initial gravitational potential energy. Then we've got the work done by the driving force, so I'm going to call that WD. Then we've got the work done by the friction, which we're taking away because it's acting against the direction of motion. And that's going to be equal to the final kinetic energy plus the final gravitational potential energy. So the initial kinetic energy is 1/2 times m times v squared. The gravitational potential energy, so assuming at the start we're at 0, okay, so we're at the ground level, if you like, then we've got the work done by the driving force. So that will be the force times by the distance. So we don't have the distance, so we'll call that x. Take away the work done by the friction, so that would be take away the friction times x is going to be equal to the kinetic energy, final kinetic energy, which hasn't changed because we're at a steady speed. So that's 1/2 times 900 times 16 squared. I've run out of space. Plus the gravitational potential energy at that point. So that's mgh. Now, thinking about this as a distance that it has travelled. So if that distance is x, and this angle is arc sine of 0.1, then this height will be x times sine of arc sine 0.1, so just times by 0.1. Okay, so that is the height, 0.1 times x. So our gravitational potential energy will be plus m, 900, times g, times by h, which is 0.1x. Okay, well, on both sides of the equation, we've got the 1/2 times 900 times 16 squared, so they're gone. We've got left over 1,250x, take away the friction times x, is equal to 900g times 0.1x. So of course we can divide through by x now, that's gone. So then we have that the friction is equal to 1,250, take away 900g times 0.1, which is 90g. And that's precisely what we had before, that's 368 newtons. So clearly of the two methods, the most working here in this problem would be using the work energy principle. This is a bit more fiddly. But just considering it from the friction point of view of resolving forces, that was easier in this problem. Okay, but in some cases you may want to use the work energy principle, and there is nothing wrong with you using the work energy principle methods within A-level maths where appropriate.